Thanks. Oh, okay. Thanks for the warning. So, and I will continue that even though it's being recorded. So, because I had to click on something, continue or leave meeting. So I'll continue. Yeah. So, yeah. I mean, I want to talk about some work that. So I was actually looking at a question in Poset topology with Carola Massaros when we were at Banff and at a program for women of algebraic combinatorics a long time ago. And you know how projects kind of wander in funny ways. And at some point I started wondering, so if we might say something about polytope one skeleta. And I want to tell you about what I think are some interesting connections between posets and one skeleta of polytopes and the non-revisiting path conjecture that comes up in operations research, and also poset topology, some connections between all these things. Actually, I want to say too that long ago, from 1999 to 2001, I was a postdoc at the University of Washington where I talked to Victor Klee, among other people, and learned a little bit about some combinatorics questions coming out of operations research from him. And so it was exciting when, like 15 or 20 years later, I thought, aha, something I'm interested in is kind of wandering back to things I learned a little bit about back then. Because the audience is from it's two different seminars combined, I'll try to give plenty of definitions along the way, and don't hesitate to stop with questions. It's complaining when I want to go to the next slide. There we go. Now it's letting me. All right, so for people in operations research, forgive me for reviewing linear programming and such, because it's a mixed audience. Okay, so, and I want to phrase things in a manner that'll really be how we want to think about things in this talk. So given a matrix A, and so what's linear programming about? This is a little toy example. So given a matrix A, and vectors B and C, we may want to know, like, what's the largest, these are all real matrices and real vectors. What's the largest dot product C dot X that you can get for a fixed vector? Well, C was already fixed and B is fixed. What's the largest dot product C dot X you can get where the matrix A times the vector X is less than or equal to the vector B? And that means each coordinate is in AX is less than or equal to the corresponding coordinate in B. Now, in the event that the set of X satisfying AX less than or equal to B is bounded, then this set of X is actually going to be a polytope in R to the D, where X has D coordinates. And here's a toy example to make this concrete. So here we have a little matrix A, and here's our vector of unknowns, x1, x2, less than or equal to this fixed vector B. Okay, and let's say our cost vector is, I don't think it, well, I guess I didn't write down the cost vector explicitly, but let's say it points in this direction I've drawn here, okay? So, then first of all, the set of valid X where we have this less than or equal will be where negative x1 is less than or equal to 0, or x1 is greater than or equal to 0, so that I have this bounding hyperplane here, and then that first inequality is going to say that we need x1 to be greater than or equal to 0. So oh, sorry, I'm looking at the wrong one. Right over here, this is x1 equals 0. This arrow indicates we need x1 greater than or equal to 0. So we're in the half space on that side of that hyperplane. And then we see negative x2 less than or equal to 0, which means x2 is greater than or equal to 0. So that gives us this other half space. We also have to have x2 greater than or equal to 0. So hence that up arrow. And then we have x1 plus 2x2 less than or equal to 2. And that means for this line where x1 plus x2 equals 2, we have to be on the side of the line that's pointed, that arrow indicates. So we have so the set of solutions is the intersection of these three half spaces, and it's this triangle. And since that's a bounded region, it's actually going to be what's called a polytope. So that's like our set of candidate vectors X, and then for our fixed vector C that I've drawn here, we want to say which of these X have the largest dot product with C. And what I've drawn is level surfaces that all have the same dot product with C. This will be where, this one is where it's the smallest, so that vertex, and then it's bigger, 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 and then it's maximized there. And so that would be the answer. And linear programming is trying to solve problems like this. And the simplex method is one approach. So in the event that your set of valid X is bounded, then, so we get a polytope, we could look at, we get from this story a directed graph on the one skeleton of the polytope. So in our polytope, okay, I have to not play with my mouse so much, I guess. In our polytope, you have vertices, you have edges, you have higher dimensional faces. Like this is a sort of more complicated picture of a polytope. So you could look at a graph just comprised of the edges you see and the vertices in this. Or here we'd have, 3 vertices and 3 edges, and this one down here, that edge, that vertex, that edge, that vertex, that edge, that vertex. Okay, and we could put a directed graph structure on it by saying that for every edge, you put an arrow in the direct that the cost increases, that where the dot product with the cost vector gets bigger. So since this has smaller cost than this, the arrow on that edge would point downward, and so on. So you get this directed graph. I'm going to denote it as G of P comma C. And we're going to assume that our cost vector C is generic. And our definition of generic is going to be that we don't have any ties as far as the cost of 2 vertices at the endpoints of an edge, so that there will be a well-defined direction on each edge, okay? So we have this directed graph on the one skeleton where we have an arrow from a vertex x1 to a vertex x2 if the dot product of x1 with C is less than the dot product of x2 with C. And in this case, the place where the dot product is maximized in the polytope is going to be the sink of our directed graph. So and so the simplex method, what you do is you start at some vertex on your polytope, and then you look at the edges going out from it and find one or look at the edges incident to it and find one that points outward, and then just follow that. And if you're not yet at the overall sink, then there'll be another edge going outward, and you follow that, and you keep going until you eventually get to the overall sink of the graph, which will be where your cost is maximized. Or you could do the reverse thing if you want to figure out where the cost is minimized. So you could walk backward on edges to the source in order to minimize. Okay, so that's kind of what linear programming, very traditionally, or the simplex method for linear programming is doing, this sort of greedy walking around on your graph. And right, so in a toy example is like so this is a different graph. Let's suppose we have 4 cities, V1, V2, V3, V4. You're probably all heard of the traveling salesman problem, where you have a distance between each 2 cities. I've written the distances in black. Then we can phrase, so you may want to say, what's the shortest path that visits each city once and returns to the city where it started? Then your choices would be the green path, the purple path, or the blue path. I hope you can tell the colors apart. And so we can phrase this as a linear programming problem by making a polytope in R to the n, where n is the total number of roads of edges, so 6 in this case. And then we make the vertices of our polytope be vectors of 0s and 1s, where we put a 1 at the locate 1 for each edge in our path. So if we think of the coordinates here as corresponding to the edge E12, E13, E14, E23, E24, E34, then in green here is the vector that would indicate the path that goes from V1 to V2, V2 to V3, V3 to V4, and V4 to V1. Purple would be the path that does V1 to V2, V2 to V4, V4 to V3, and V3 to V1. And blue would be the other path cycle, okay? And if you think of, and then what I've done is I've made a cost vector where each of the coordinates is the cost of using that road. And then if you think about it, if you take the convex hull of these 3 vertices in R6 and you look at the cost, so if evaluating the cost, the dot product of C with this vector is going to give us the cost of the green path. the sum of the distances. This C dotted with this gives us the sum of the distances for the purple path. C dotted with this gives us the sum of the distances for the blue path. So, minimizing the cost vector dot product with X for points in the polytope is going to say what's the cost of that linear combination of roads, or it'll actually be a non-negative combination of roads. And geometrically, you can probably not be surprised to hear that the max or the min always has to be at one of the vertices. So in particular, you'll get the shortest path by just trying to minimize this dot product on the polytope. That's the convex hull of these three vertices, okay? So, okay, and tiny bit more background. So a polytope, more formally, is the convex hull of in R to the D, you can define it either to be the convex hull of a finite number of vertices. So, that means for any 2 points. So for two of the vertices, you draw the line segment between them. And then for any 2 points in the polytope, you have to draw the line segment between them. Equivalently, if a polytope is any bounded subset of R to the D that is an intersection of half spaces. So that means you take a hyperplane and take all the points on one side, take another hyperplane, take all the points on one side, and intersect these. So that was like our thing where you said, well, for this line, we're on this side of it, this line, we're on this side, and this line, we're on that side. So these are two equivalent definitions of what's a polytope. And then, okay, now is a definition that's going to be really critical for this talk. A polytope is going to be simple if, say it's a D-dimensional polytope, okay? Which is, I don't mean that it's in R to the D, I mean that the convex hull is D-dimensional. So that if you look at like the interior of the polytope, that'll be homeomorphic to R to the D is what I mean by D polytope. If you have a D polytope, we say it's simple if you have a D, like say we had a 3-dimensional polytope, whenever you look at a vertex of your 3-dimensional polytope, you need there to be at least 3 edges emanating out from that vertex in order for it to be possible for it to be 3-dimensional. I mean, you could have 4, but you definitely need at least 3, right? So we'll say a polytope is simple, a D-dimensional polytope is simple if for every vertex and every set of, or let's see, I guess I want to say that, so I'm given a vertex and given a set of R edges emanating out from that vertex, I want there to be an R-dimensional face in the polytope that contains that vertex and all of those R edges, okay? So this here is, so this vertex V and these 3 edges, E1, E2, and E3 are just fine because we have a 3-dimensional face there. These 2 give us a 2-dimensional face and so on. But this here is not okay because this vertex V, if you look at these 4 edges emanating out from it, well, there's no 4-dimensional face with those, but let me say, you can already see the problem by taking like 2 opposite edges, like this edge here and this edge here. If they were going to give us a 2-dimensional face containing the vertex and those 2 edges, it would contain this triangle. And the problem is it cuts right through the middle of the polytope, right? And faces are things on the boundary. A face of a polytope is the intersection of a polytope with what's called a bounding hyperplane. So like this edge, you could have lots of different choices to your bounding hyperplane. But so anyway, we're going to take this isn't the only definition of simple, but for us, a good definition of a simple polytope is that whenever you have a vertex and you have R edges emanating out from it, you actually get an R-dimensional face of the polytope that uses them all. So, okay, so now back to the simplex method. So in linear programming, if you're walking around on the polytope trying to reduce, walking around on the one skeleton, following the directed edges to keep increasing your dot product with the cost vector, one thing that gets a lot of attention in OR is things called pivot rules. And what that is if you're say you're at a vertex V and there's a whole bunch of directed edges going out from it, then a pivot rule is some kind of rule to decide which of those directed edges should you follow. Like you might think, well, I'll just take the one that increases the cost the most because that's likely to get me to help me get to the sink faster, right? People are concerned how long it takes. So anyway, but there's tons of work over many decades on trying to pick good pivot rules. So a couple questions that people have cared about for a long time is, what's the typical complexity of the simplex method? How many edges are you going to need to follow? And what's the worst case? If you made really dumb choices for your pivot rules, how long might it take? Okay. So now the Hersh conjecture, and it's spelled differently than my last name, so it's not me, it's way before me, is a conjecture about diameter of these graphs you get on the one skeleton of a polytope. Okay, so given a d-dimensional polytope with n facets, so a facet is a maximal face of the boundary. Okay, so like if you have a 5-dimensional polytope, its facets would all be 4-dimensional. So given a d-dimensional polytope and let n be the number of facets in it, then the diameter of the one skeleton as an undirected graph, denoted delta of d comma n, is always less than or equal to n minus d. This is a conjecture that was around for a very long time. Finally, after decades and decades and decades, Francesco Santos found counterexamples to this. He constructed counterexamples. And one of the ideas that went into his construction was something called spindles. And these are polytopes where you have two vertices, V and W, such that every facet of the polytope either has V in its boundary or has W in its boundary. So they look something like this. So he started with some polytopes like this, and his first example, and he was able to get counterexamples out of particular ones, with partly using, there was some really insightful ideas, but, and some computer work combined with it to verify his examples. But his first example had 43 dimensions, it had 86 facets, and he could prove its diameter was greater than or equal to 44, okay? So anyway, this is kind of a framework for what I want to talk about, some history. I'm almost to saying what our plan is, or a big part of our plan for the talk. So let's see. But another conjecture that's related to the Hersh conjecture is called the non-revisiting path conjecture. It says whenever you have two vertices u and v in the boundary of a polytope, there exists a path from u to v that never revisits any facet that after leaving that facet. I just realized I should have a picture here. So let's see. Okay, so it would probably help to, I'm sorry I wasn't organized enough to have one planned, but I was just looking for a good picture to work with. So I guess I'll use my fingers. Okay, so say you have a cube, or I guess I do have a picture of a cube here, right? So like, look at this face over here where the x coordinate is 0, right? That's one of our facets, right? If you're at this vertex and you follow this edge, then you depart from this facet. That's what I mean by departing a facet, right? So you go from a vertex. So this vertex is actually in 3 different facets. It's in that facet, it's in this front facet, and it's also in this bottom facet. If you follow that edge, you leave the bottom facet. If you follow that, you leave the x equals 0 facet. And if you follow that, you leave the front facet. Okay, so that's what we mean by leaving a facet. So the conjecture is that whenever the non-revisiting path conjecture is that for every 2 vertices u and v, there should exist a path from u to v such that whenever it departs from a facet, it's not going to return to that facet before, And that sounds like, well, of course you should be able to do that. Like in this example, you can. In this cube, you can do it no problem. Like to get from 0, 0, 0 to 1, 1, 1, when, once you leave the bottom facet, you don't have to come back to it, right? So, okay, anyway, but in fact, the non-revisiting path conjecture implies the Hersh conjecture. And so once we knew the Hersh conjecture was false, then it meant the non-revisiting path conjecture also had to be false. And there's a really simple argument of this implication, because the point, let's go back to our Hersh conjecture in this diameter bound, right? So let's say, so if we have n facets and d is our dimension, then because let's see, so every vertex has to have at least d facets adjacent to it, right? So if you think about it, because it's d-dimensional, and so the first vertex has d facets adjacent to it, the last also does. Every time you follow an edge, you depart from a facet, right? So you have n facets to begin with. If you suppose you took more than n minus d steps, then every time you follow an edge, you depart a facet. But at the end, your vertex is still contained in d facets. So you can only take at most n minus d steps if you're never allowed to revisit. So that's why non-revisiting would imply Hersh. So anyway, so they're both false. And a related conjecture is that the strong monotone path conjecture, that there exists a directed path of length at less than or equal to n minus d from any vertex v, let's see, any vertex to the vertex v that maximizes the cost, c dot product with v, with cost increasing at each step. I'm not going to address that conjecture, but that's kind of getting, if you think about it, the diameter is certainly related to this directed diameter that we're interested in. So, Santos proved it's hopeless for polytopes in general to have these, this n minus d diameter, or to have this non-revisiting path conjecture. He proved that's hopeless. What I became curious about is maybe we could impose conditions on, maybe we could sort of understand conceptually if there are nice conditions on a polytope P and a cost vector C that would imply something even stronger than the non-revisiting path conjecture. Maybe you could say that, well, if P has these properties and C has these other properties, then no matter what directed path you pick, it never will revisit any facet that it has left. Okay, and that's I conjecture what some conditions may be, and while that's still open, I've proven a corollary of the conjecture, which I think is evidence, and a bunch of lemmas towards the conjecture, and I really believe the conjecture. So, yeah.
Hi, this is Jesus.
Yes.
So the strong monotone path conjecture is false, right? I mean, Mike Todd has this counterexample of a four-dimensional polytope.
Okay, thank you. Hey, I didn't know you were here, and you know what? I couldn't remember, so that, okay, and that's why I sort of, I stated it, and then I couldn't remember. Yeah. So thank you for filling that in.
My comment is that in some sense, the directed version of the Hersh conjecture is known to be false way before Paco Santos found the counterexample for the undirected version, right? So
okay, that's great. So, but there's still the question of, can you give nice classes of polytopes?
Right,
right. And I'm actually even looking for the stronger thing that I want, like that no matter which choices you make, it goes well. Mm-hmm. That you never revisit a facet you've left. And by the way, never revisiting a facet you've left is equivalent to never revisiting any face of any dimension that you've left, because faces are intersections of facets. So, and that's how I'm going to think about it a little more. But so, okay, great. So, and this is one of the, yep, this is one of the, thank you very much, Jesus. I didn't know you were here, but I appreciate your helping out there. So, yeah, so one of the conditions that I suggest for a polytope is called the Hasse diagram property. And one way to say what it is it says that you can never revisit an edge after departing from it. So say we have this edge in the one skeleton, you can't have some alternate path where you have an edge that leaves that edge, you take some more directed edges and you come back, okay? And again, we're using the directed graph. So we say G of P comma C has the Hasse diagram property if it is the Hasse diagram of a finite poset, i.e. if you have V1 directed edge to V2, directed edge to V3, dot, dot, dot to VR for R greater than or equal to 3, you cannot have a directed edge straight from V1 to VR. There's no shortcut. So these are called cover relations. And in a partial order, if V1 were less than or equal to V2, less than or equal to V3, then transitively that would imply V1 less than or equal to VR. And so we wouldn't draw that edge in the Hasse diagram. So it's why I call it the Hasse diagram property, but it's exactly the non-revisiting of one-dimensional faces. Now, a very sad thing is that the Hasse diagram property says your polytope can't be simplicial because you can't have any simplices, right? So you can't, because two simplices would fail. So it rules out a lot. Here's a hypercube, and that works fine. And in this case, directing the edges where you're changing zeros to ones. And in this case, we get the Hasse diagram of a Boolean lattice. Okay, and on the other hand, the Klee-Minty cube is famous as the first example that you could have really, really bad. The simplex method could work really, really badly. I've drawn in purple and red here a way of realizing a three-dimensional cube inside a standard cube. I basically lifted this picture out of a paper of Gartner, Hank, and Ziegler. And if the cost vector is going up, then you would go like this. And I want to point out that this very badly fails the Hasse diagram property. You could see it in this green face here, right? So that you keep departing from face to, edges and coming back to them all over the place in this example. So I mean, this gave me some hope that the Hasse diagram property is getting at something. And I kind of wonder if what's going on with non-revisiting of low dimensional faces might propagate up to higher dimensional faces that are tougher to look at, but or to see what's going on. But anyway, so Klee-Minty cubes do violate the Hasse diagram property in a way that really seems to get at what's going on with this long directed path that visits all 2 to the n vertices. And the Hasse diagram property would block out examples like this, at least. And I want to mention that the permutahedron, if you can put a cost vector on it like this, and then here I've taken the standard realization of the permutahedron, and then the Hasse diagram this has the Hasse diagram property, and in fact you get the Hasse diagram for weak order. The associahedron, using Loday's realization, the one skeleton with an appropriate cost vector, then the one skeleton gives you the directed graph gives you the Hasse diagram for the Tamari lattice. And I would point out that both of these posets, the weak order and the Tamari lattice, have order complex homotopy equivalent to a sphere for each, or every interval will be homotopy equivalent to a ball or a sphere, and they can characterize when you get which. And you can actually recover those results from what we're going to do a bit later. Okay, continuing. Okay, that was weird. Sorry, I'm not the Zoom master. I don't know how to get, okay, well, let's see. Full screen, there we go. Okay, so here's a lemma about propagating up in dimension. It's going in a slightly different direction, but let's see, suppose you have let's see, what do I have here? A simple polytope P and a generic cost vector C such that the graph, the directed graph G of PC is a Hasse diagram, okay? Suppose we have a face F contained in a face G. So I've indicated, like, say F is this purple 2 face and G is this 3-dimensional blue face that contains F. Then there cannot exist, it's not possible, this will sound a little technical, but it's pretty useful. It's not possible that you have vertices V and W in your face F and a directed path from V to W such that the unique edge of G that is involving V that's not contained in F. So, so since G has dimension 1 higher, there's going to be a unique edge that's an incident to V that's in G but not F. If you can't have that edge goes out and that the unique edge emanating from W goes into W. And it's really easy to prove this, because what you do is that you'll have a unique, if you look at this path, at each place you'll have a unique edge that goes into G from F, and it either goes in or out. And if you start going out and you end going in, then at some point you have to switch from out to in, like out immediately followed by in, by the discrete intermediate value theorem, the discrete version. And when that happens, you'll have a two-dimensional, you can prove that you have a two-dimensional face here that contains both this edge and this this vertex will be the unique source of that two-face, this will be the unique sink, and you'll have this path from here to here and this other one, and you'll violate the Hasse diagram property. Voila. So that seems like a tool that you could work with some. And you can get as a corollary of this that any face of your polytope that either includes the overall source or the overall sink will have any face F containing either the overall source 0 hat or the overall sink 1 hat will have the property that faces that depart from that face, or sorry, paths that depart from that face can never revisit that face. Okay, so you get those cases. And in fact, that basically buys you spindles, because in spindles, well, at least if you picked a cost vector where the two key vertices of your spindle are the source and the sink, then every facet would contain either the source or the sink. And so that gets you the non-revisiting, or that shows that I guess from that you can show that that the spindles cannot possibly satisfy our hypotheses. Sorry, I misspoke, because we know that they can't possibly satisfy our hypotheses if you use 0 hat and 1 hat as your source and or these two distinguished vertices as your source and sink. And so you can get, I'm not saying this very well, but you can deduce from that spindles aren't going to be the counterexamples of the type Santos found for the non-revisiting path conjecture and the Hersh conjecture are not going to be counterexamples to my conjecture because they won't meet my hypotheses. Okay.
Can I ask you a question, Tricia?
Yeah, sure.
So I see why the spindles themselves don't satisfy, but in the construction of Paco, they still have to blow up some vertices, right? They have to do some other things.
That's right. But yeah, I looked through it carefully. Yeah.
So those operations don't mess up. So still, they are not Hasse diagrams in some sense. So what you're claiming is that they're not Hasse diagrams.
Right.
Okay.
Yeah.
That's nice.
Yeah. So yeah, and I'll be happy to talk with you more later. Mm-hmm. So yeah. So okay. So let me remind you. So that a lattice. So right. So that's one thing. And now I want to kind of connect to some more. You know, I said that I'm going to get a corollary of this statement here, right? So I want to get to the corollary, and I'm going to throw in another hypothesis. So far, I've been saying simple, and I've been saying Hasse diagram property. And for the corollary, I want another hypothesis. I want this not just to be the Hasse diagram of a poset, but of a lattice. And by the way, it could be some things would still hold without this hypothesis, but this is where I can prove something, okay? So, and so let me remind you, a lattice is a partially ordered set where whenever you have two elements U and V in your poset L, there exists a unique least upper bound for U and V, which we call the join, and we denote it like this. You can think of that as some sort of like a union symbol. And there's a unique greatest lower bound, something that's below both. We'll call that the meet and denote it like this, okay? So next thing I want to observe is if you have P is a simple polytope, and you have this as a Hasse diagram, then it's always going to be the case that if you have an element X that's covered by U and covered by V, that so if it's a simple polytope, we know there's going to be a two-dimensional face that includes both those edges, right? And if you think about it, the sink of that two-dimensional face S is an upper bound for U and V, right? And one thing I became interested in is, will that be the least upper bound for U and V? Is it possible that there's some other smaller, you know, that you have some path that wanders off of this two-dimensional face and some, you know, wander off from here and they both get to the same thing that's actually strictly less than S, right? So, so we're going to kind of think about whether, so the question I want to think about now is whether this kind of upper bound you get by taking the sink of the smallest face containing these is actually the least upper bound. And it's certainly related to the non-revisiting path conjecture because, okay, so let's define, so given a simple polytope P and a generic cost vector C, where this is the Hasse diagram of a poset, I didn't say lattice, just a poset with x1 and through xr elements of the poset that all, such that there exists an element u in the poset that are all, that's covered by each of these elements. So you can think of it as you have u, x1, x2, x3, and so on, all covering u. So then, okay, and this is just to remind you of the notation. That's what I mean by covers, that it's immediately above. And an atom is going to be of a poset closed interval is something that's immediately above the bottom, okay? Then with this notation, we say that the pseudo join of these elements x1 through xr is the sink of the unique r-dimensional face containing all these edges, right? So if we have this U covered by x1 and x2, then this would be the pseudo join of x1 and x2 within the, with respect to the, thinking of them as covering U, okay? So, so in any interval upward from U in the poset. Okay, then here's a lemma. For P a simple polytope and C a generic cost vector such that this directed graph is the Hasse diagram of a poset L, if S and T are two different subsets, are distinct subsets of the set of atoms, so the things that are covering the bottom, then the pseudo join of the set of things in S is not the same as the pseudo join of the set of things in T, okay? So, and in the case of a lattice, this also holds for the atoms of any closed interval within the lattice. A corollary of this is that the subposet of pseudojoins within your overall poset L is isomorphic to a Boolean lattice of the, where you can identify the elements with the various subsets of A1 through AN. And I won't go through the proof, but I've written on the slides a little bit of the idea. You can reduce to the case where you go up by one, where S is a subset of T, where T has dimension exactly one more than S, and then you can use my non-revisiting lemma that I already did, where you go up by one in dimension. Okay, so we have that at our disposal, that this distinctness. And since the, let's see, like I said, since the pseudo join of x1 through xr is an upper bound, that whenever we're talking about a lattice, there will exist a directed path from the least upper bound, the join of x1 through xr, to the pseudo join, right? So if they're not the same, there has to be a directed path from here to here. Since this will be less than or equal to every upper bound, and this is an upper bound. Okay, so here's another theorem. If P is a simple polytope and C is a generic cost vector, where our directed graph is the Hasse diagram of a finite lattice, and this one is I think one of the main theorems, then the pseudo join of these atoms actually equals to the join of these atoms. And we can say that for the various intervals in the poset too. So, and the proof is by induction on R, and the base case where R equals 2 is actually the toughest part of the whole proof, I think. And here's a picture that hints at how the R equals 2 case works. What I want to say is that, you know, suppose there existed a U covered by X and Y where the pseudo join of X and Y, V in this picture, is not equal to the join of X and Y, right? Then the join would have to be it's easy to see it would have to be outside of the, well, I guess there's cases to consider whether it's outside of the face. What is easy to see is that for sure you'd have to have directed paths that depart the face at some point. So you can't just stay within the face, right? So let's suppose the join was out here somewhere, then, you know, there's some argument here. But also I want to say what the induction is on, okay? So, or I mean, this is a different type of induction now. So suppose we have a U and covered by elements X and Y where the pseudo join of X and Y does not equal the join of X and Y. Then I want to associate to this the length of the longest path from U to the overall sink, 1/2, right? So for this U, we can say, what's that length? What's the length of the longest path? I'm not assuming graded. What's the take the longest path. On the other hand, if we had a V that covered two elements, you know, X prime and Y prime, where the pseudo meet of X prime and Y prime was not equal to the meet of X prime and Y prime, then we could associate to this the length of the longest path from 0 hat up to V, right? And what we want to do is say, if there's a counterexample of either type, we want to pick one that minimizes this quantity, this length of longest path. And without loss of generality, we can assume it's a join that's problematic, okay? And now you can use that to sort of somehow argue with things I've already said, that you can get a contradiction. That, like, you know, say that we're going up this way and we depart at some point, then, you know, we get this two-face here, and we can argue that this pseudo join actually has to be the join of these things, blah, blah, blah. And, you know, anyway, I could talk it through more if anyone wants later. Now I'm gonna, okay, so anyway, but this theorem, if we did have the non-revisiting path conjecture, or sorry, if we did have this non-revisiting, strong non-revisiting, I'm conjecturing, you know, for a simple polytope where the directed graph is the Hasse diagram of a lattice, if that always implied that that directed paths can never revisit faces after leaving them, then that would imply that the pseudo join equals the join. So here, this theorem is a corollary of that conjecture. Okay, so, okay, now I switch gears just a little bit. The order complex of what kind of got me actually first thinking about these things was some Poset topology. And I want to connect with that and say how it might hint a little bit at like what polytopes could have our properties in a loose sort of way. But okay, so given any partially ordered set P, we associate to it an abstract simplicial complex called its order complex, whose I-dimensional faces are the I+1 chains, so chains of I+1 elements, each less than or equal to the next. So if we have this Poset P, we get 6 vertices from the elements, we get 6 edges, or sorry, we get edges from more than 6. We get the edges from the 6 cover relations, but we also have an edge from like 0 hat to A2 because 0 hat is less than A2, and so on. So we get like 0 hat less than A1 less than A2, that's a 4 chain, so that gives us a 3-dimensional face here, and we have this 3 face, and so on. So it's an abstract simplicial complex. And one reason people care about these is because the Mobius function of the Poset can be interpreted as the reduced Euler characteristic of this complex. What you do is if you want to do the Mobius function from U to V, you look at the interval from U, let's say U equals 0 hat to V, say V equals 1 hat, and take the proper part, you chop those out, and take the order complex of the sub-Poset. So like, that would be the green thing for the example I just described, the pair of edges. And the reduced Euler characteristic is -1 plus number of vertices, minus number of edges, plus number of 2 faces, and so on. And you can use like shellability and things sometimes to calculate the reduced Euler characteristic and get the Mobius function. One of the tools people like to use to study order complexes is the Quillen fiber lemma. What it says is if you have an especially nice map from a Poset P to a Poset Q, then the order complex of P should actually have the same topology, be homotopy equivalent to the order complex of Q. And so what you can do is if you give a good enough Poset map to meet your hypotheses, and say you already understand what the topology of Q is, you can say, well, then I can figure out from that the topology of P, or vice versa, right? And this has been used, and I won't go through how it works, but it's been used extensively, like in finite group theory, to characterize different group properties, for instance, for subgroup lattices, the Poset of all subgroups of a finite group. So we're going to use the Quillen fiber lemma to say something about these Posets coming from one skeleton of simple polytopes, okay? So let's suppose P is a simple polytope and C is a generic cost vector where our directed graph is the Hasse diagram of a lattice. Then the order complex of every interval in this open interval in this lattice is either going to be homotopy equivalent to a ball or a sphere. So that implies, for instance, its Mobius function is always 0, +1, or -1. And we do this by using a poset map that takes any element of our poset X. And what you do is you look at the, let's see, we're studying the interval from U to V right now, right? So take some element X in the interval from U to V, then look at all of the things, all of the atoms of that interval. So the things that cover U and are less than V, take the join of those, and that's what we're going to assign it to X. And by our previous theorem, that's going to be equal to the pseudo-join of these things. And we can use our result about distinctness of the various pseudo-joins to get that the image of this poset map is a Boolean lattice. And it either includes its maximal element or doesn't, depending on whether V actually equals the join of the atoms, since we're taking V out, okay? And so from that, we can get that the order complex of that open interval is homotopy equivalent to either the order complex of a Boolean lattice with its top and bottom chopped off, or with the top left in, so either a sphere or a ball. But one thing I want to remark is that the hypotheses here are the exact same hypotheses as I have for my conjecture. And so, you know, one thing you might say is that if you had I don't know how easy this would be to check, but if you had a polytope and the directed one skeleton, and you could prove that its order complex was not homotopy equivalent to a ball or a sphere, then you know it can't meet these hypotheses, right? And so the ones where you get balls and spheres are the ones that have a chance of meeting my hypotheses and possibly having this really strong notion of phase non-revisiting. So as some examples, that, you know, these are very special, but the permutahedra with the cost vector I mentioned, and the associahedra, and also generalized associahedra, and these are related to cluster algebras, they all satisfy these hypotheses. So they all will have the kind of good non-revisiting of faces. And the associated posets are the weak order, the Tamari lattice and Cambrian lattices. So it gives a unified proof for all of these that every interval has, of the poset has order complex homotopy equivalent to a ball or a sphere. And I'm almost out of time, but I will say that zonotopes are, you know, zonotopes people already know a lot about, but those are really well behaved under these, in this story. That if you have a zonotope and a generic cost vector, then this will, or with the, let's see, what do I say here? Any zonotope P and generic cost vector yields a directed graph with the non-revisiting property, hence the Hasse diagram property. And that's a Minkowski sum of line segments. And in my paper, I get into a little more about what's going on with the case of zonotopes. Vic Reiner suggested to me working in a slightly more general setting than just the cost vectors, that you could use something called facial orders. I won't talk about that, but in my paper, I say a little more about that level of generality. And Lou Bolero, one obvious question, nagging question is how easy is it to check this Hasse diagram property? And I was chatting with Lou Bolero about that. And this, I mean, this doesn't mean it's easy, but by any means, but you could look at the directed adjacency matrix and raise it to the rth power, and you can express this in terms of some linear algebra data then. But yeah, but let's see, the big question is, does P simple and this directed graph Hasse diagram of a lattice imply that no directed path can revisit any face after it has departed from it? You know, and one could ask about variations on the hypotheses, such as non-simple polytopes. I've played around a little bit with the poset topology for non-simple polytopes, but don't have theorems, but I feel like some of the things may still sort of hold. And non-lattices, this conjecture, I mean, I don't know if lattice is needed. It's needed for the corollary to make sense. Right, and let's see, and you could, yeah, and you could just try to understand the structure of the posets you get on the joins and pseudo-joins for non-simple polytopes too. I think I'll stop there, but thanks a lot.
Thank you so much for your talk. I wonder if we could all unmute ourselves and give Tricia a hand for her great talk. you. So I will now open the floor if anyone has any questions.
So Tricia,
Yeah.
so right now you know permutahedra, associahedra, sonotope.
Generalized. Yeah.
What other
Oh,
things?
I forgot. One can also get low dimensional polytopes. I haven't, so.
Yeah, I was going to ask you whether you can get, for example, two-dimensional polytopes this way. Sorry, three-dimensional polytopes, I meant.
Yes, because you can get it pretty easily out of that lemma that with the 2 faces and 3 faces and 1 faces.
Mm-hmm.
Yes, you can do 3 polytopes. Yeah.
Now, if I understand correctly, everything you develop is for simple polytopes, right? So far?
Yes. Right, right. And
I mean, those are the most popular ones anyway in linear programming, because those are the ones that people use in practice. So that's okay.
yeah, I just felt like, I mean, to me, intuitively, I felt like they were the ones I could work with. I felt like the property of being a simple polytope plays really well with the Hasse diagram property. I keep feeling like I should be able to prove more. I mean, honestly, I haven't had time to work on it in like the last year because of moving and COVID, blah, blah, blah. But I feel like, I mean, it's very tantalizing to try to prove more. But basically, I picked these hypotheses because they're the ones that I could do something with. And I thought that they were not totally crazy hypotheses.
Yeah. I have one common question. So,
yeah.
So as I think you know, Vilera, Kapranov, Stunfels, they study this monotone path polytope, and they define a simplicial complex. There's a Bowes complex of sorts. So, I mean, it's a natural question. Is there a connection between what you're doing and that Poset topology there?
I have wondered about that. I mean, because they have these non-coherent strings, right, and things.
Right.
So, or I forget. So, yeah. I have to confess, I kind of pulled this talk out, even though I haven't been deeply thinking about this recently. But
so I think that would be fascinating because
yeah,
I mean, they proved that poset. I mean, essentially the vertices of the poset, the 0 faces of that poset, are all monotone paths of the polytope, right? So some of them will be coherent, and therefore they belong to these fiber polytope. They are
right.
But it seems to me that maybe you can really connect these two things. I mean, it sounds very, very related to each other.
Yeah, I've been wanting to try that. In fact, now that I've moved to Oregon, there's all these great algebraic topologists here. I've been hoping to sit down and brainstorm maybe.
All right.
Because they'd be better at that side of the story, right? And but yeah, I've been wondering this, but just haven't had really time to look at it yet. So, yeah, good question. Yeah, so this project is in the same, well, I guess I dealt with like the spindles and the low dimensional polytopes in like the past year. But other than that, it's kind of like sat where it was for a little while just because moving was very time consuming.
So in some sense, what you also want is to look at this, if you look at the order complex, you want to find simple polytopes for which the order complex, so they are Hasse diagrams, I mean, you have Hasse diagrams, but yet when you look at this order complex on the interval, you get some nasty behavior, right? That would be something to try.
So in order to find counterexamples or what?
Yeah, because if you can put back your theorem, the last theorem you had, I mean, I guess before the open, that one, yeah. So there you said that that's a necessary condition, I guess, no?
Right, that's right. So, oh yeah, right. If one wanted to look for counterexamples, then one could try to find them topologically. Is that what you're saying?
Yeah, yeah, exactly.
Yeah, that's right. Yep. That's right. Yeah, and so that's why I wanted to highlight that this is the exact same hypotheses as the other theorem. So it's not like one thing implies the other, but it indicates some relationship. And as you say, that could be a good way to look for counterexamples, or it's a different way.
Right.
Yeah. Right, so the goal here was to kind of be conceptual. And by the way, I mean, another thing I've wondered about is whether any of the famous polytopes from OR actually satisfy these hypotheses. I haven't had a chance to check really. I mean, and some of these things aren't the easiest thing to check either.
Right.
But I would love candidates.
Yeah, no, it's nice. I mean, I'll think about it.
Yeah, I mean, and yeah, be in touch if you want. I'd love to chat about it.
Of course. Yeah.
Yeah, right. And now I'm actually I predict that my first like right now I'm not traveling anywhere, but I'm more likely in a year or two from now to travel by car than to be flying all over the place. And Davis is not so far.
Right. Although right now everything is far.
Yeah, right. But yeah, see, since I went to this conference in Florida where I gave these 2 talks, and after I got to Florida, they like started shutting down the country. Everything happened so fast, and I was scared. How am I going to be able to fly back from Florida to Oregon? And so this is why car travel seems more appealing at this point.
Yeah.
Can I ask a basic question about it's a couple slides before this one, the corollary about how the subposet of pseudojoins is a Boolean lattice.
Yeah.
So I don't know a lot about posets, but that just seems interesting. Are there other cases or situations where some natural subposet is a Boolean lattice, and what does that tell you about the?
Yeah, there's various cases. I mean, there's actually this trick I use here where I'm taking this like, the poset map I use here. Let me find it. This one, like this trick I've seen in other papers, like, in other contexts where you'll prove a poset is, its order complex is homotopy equivalent to a ball or a sphere via a map like this and getting a Boolean lattice this sort of way. So, yeah. Right, it kind of comes up in like my work with Carola Mizaros on SB labelings. We have a joint paper that was kind of out of which I wandered into this project, while working on that. But yeah, I've seen other things. I mean, some proofs regarding, Cambrian lattices and things.
I think we may have time for one more question if anyone else has any questions.
Thanks for having me, by the way.
Yeah, I was just about to say, let's thank our speaker again. Yeah.
And
Thank you for joining us.